The stage is yours.
Okay. Yeah, thank you very much. Yeah, so I need to share my screen. So here, also this is here. This is already the. So here, I hope you can see this. All right. Yeah, so thank you very much for the opportunity to give this talk here. I'm from Tokai University. It's a minor university, not so famous like Waseda, but also in the vicinity of Tokyo. So thank you very much. Also the talk is the active role of carbon nitride and carbon quantum dots for photocatalytic water purification. And this is a literature overview. So I hope I can share this here. So also this is the aim of the talk, sustainability. I will talk about these 4 topics, photocatalytic mechanism, and then water purification and methods for optimization. Also the is from the abstract, water purification by degradation of organic polymers have improved over the last decades as the important parameter for performance, such as nanometer size, high absorption factor, slow recombination rate, high carrier concentration, PN junction, and high carrier mobility. And actually, in September, we had the first carbon material nano symposium, and I don't want to repeat all the features from the first video, so please look at the first video if you want to have a more insight in this parameter. So today I will talk a little bit different about carbon quantum dots and graphitic carbon nitrides, and they have increased in the last 2 years because they have a low cost of processing and easy processing. So, and of course, there are already some reports, 100% degradation of dyes, bacteria, or virus within less than 10 minutes. But there are also papers which require a longer time or a less degradation. But any basic research on this field is welcome, because it is so important subject for our daily life. Also, the closer to humans, the less poisonous the material should be, and with this light, we can purify the water. So I need to go to the next slide here. So this is a general overview. There is a lot of discussion now. It is the buzzword, the Great Reset. Also in this time paper, all the sins from the last decades, like pollution and plastic production and so on, and virus, this should be reset now, and especially in the sector of energy. There are the 4D transformation, decarbonization, also not use of any fossil fuel anymore, then digitalization, the transition from analog to artificial intelligence. This will save a lot of energy, and all the big companies in Japan like Hitachi, Toyota, and Mitsui Fudosan are building now smart cities to show in a small environment how to develop the artificial intelligence for the cities of the future. And then decentralization, small scale power plants, and democratization. So also there should be a lot of public funding, and so this is the next slide here, the Sustainable Development Goals developed from the United Nations, and water purification is one of the most important issues. I mean, it's not so important in Japan, but in a lot in desert areas of the world, this will be a big issue in the future. And so carbon quantum dots are one of the materials, and carbon quantum dots have a big advantage. They can be produced from natural materials. Also if you fry a steak on the barbecue, then it is most likely that there are some carbon quantum dots there formed in nature. And if we use natural materials, then we can also use them as biosensor or for drug delivery. So this has also another important issue. If we would get more basic insight into the carbon quantum dots, then they can also be used for medicine, as shown in many overview papers. So also this was the slide from the first talk. The method which I was using, I did a literature search with Scopus and found so many papers, and alone in the year 2020 there were more than 1,200 papers, and so I think by reading these papers and giving an overview presentation on these papers, we can stimulate also young researchers to work on this field. And also I'm talking about degradation, this orange color here, but all these other fields are related. So biosensors in green, chemical catalysts, water splitting, and solar energy is all related. So also this was the mechanism. I just want to show the excited state in the next slide. So please look at the first video if you are interested. So also these are the optical properties of any material. There are three parts: reflection, absorption, and transmission. And depending on the wavelengths, each of these parts can be stronger or weaker. And now the people who designed the windows for public transport, like railway cars, they found out if we put some gold nanoparticles into the glass, then we can reduce the ultraviolet light which comes into the train. This is called the UV cut windows by gold particles, and this of course is now standard at any vehicle to reduce the heat radiation in summer. When the temperature is so hot, there should be not additional heating from the UV radiation. And also the smart windows is a different issue. This is already used in Singapore in the light railway since more than 20 years. This is based on TCO. This is transparent conductive oxides, which make it possible to put electric voltage, and then the window shuts to blind mode, and this protects the privacy of the people who are living in this area, so that there are no private issues. So what we are talking today is about luminescence. This is the excitation by strong energy beams, UV light, and then as a function of time, this excitation is decaying, and this additional energy causes the material to chemically transform into other states. So this is the magic behind the photocatalytic effect. And also this shows now the overview. Gold and silver particles are known since the medieval ages. This is here in reviewed in this paper, the stained glass at the Cathédrale Notre Dame in Paris. In the 15th century, they had already technology for gold and silver particles. And gold is very expensive. So in the last 20 years, the research was changed to zinc, cadmium, selenide, sulfide. So all the nanoparticles could be produced in with photoluminescence in this region also. And then in the last 2 years, the carbon quantum dots were available. This is, for example, in this overview paper. So from the expensive metallic or semiconducting materials, we come now to the cheap carbon quantum dots. And this makes it possible to apply the same features for water purification in a much more green technology. And also I just show some examples of conventional photocatalytic materials. They are mainly based on silver and titanium oxide, and usually the band structure is shown here. Also we have two composite materials, and in one material electrons are excited and then give the electrons to the chemical reaction so that it can proceed and degrade the polymers. And since a few years, the graphitic nitride came into change, and this is one of the first paper who mentioned the active role of the carbon nanoparticles. Here the band orbitals can contribute to this mechanism, and also carbon quantum dots attached to zinc oxide is published in this paper. And of course, there are many other features. You can focus the light stronger so that you can get a more higher energy. And so in today's paper, I will just discuss some new features. This the type of band structure of photocatalytic materials as found in conventional semiconductors. Type 1, the band gap of one material smaller than the other, then the two band gaps attached to each other, and type 3, completely different range. And instead of this overtaking the electrons in such a way from the highest occupied orbital and the lowest LUMO orbital, this set scheme is proposed that the silver metallic particle can take over the electrons from this conduction band to this valence band. Also, so excited electrons are the main issue for this. And now the active role of graphitic carbon nitride is shown in this paper for the first time. It's already from 2017. So there are many orbitals, and iron, sulfur, phosphor, oxygen, or carbon doping change the band gap a little bit. So that is beneficial for the design of the photocatalytic material. And so this is a famous graph which is shown now as a to convince everybody that nanoparticles are so important. It shows on the x-axis the number of aromatic rings, and the smaller the particle gets, the higher gets the band gap. Also this sounds first as a bad thing because you need a stronger energy to excite the electrons. But on the other hand, this 2014 Nobel Prize on the light emitting diodes showed the higher band gap has also the advantage the material becomes more reliable and the quality of the material is better. So these are the active roles in the nanoparticles, and I'm planning to write an overview paper on this, all this summarized. So in the among the research is a big question: what are the differences between the different kinds of carbon nanotubes? We have CQD is the carbon quantum dot, then the graphene quantum dot, GQD, then just carbon dot, CD, and quantum dots or nano dots, and another one is polymer dots also. Also, first, it is all about the atomic bonding between the carbon atoms. This is a crystalline material in 3 dimensions, and which shows the Raman peak at 1,100 inverse centimeter. And the graphene quantum dot are 2-dimensional materials. Graphene has so much was focused on so many research papers in the last years. So it shows a D band and a G band at these energies. And then carbon dot is a more general expression. It can be any carbon and it is usually considered as amorphous. So amorphous means it's not so well defined, and so many, there are already also some overview papers where the students get frustrated because they always get amorphous material instead of the well-defined crystalline material. And so it is advised not to give up, but still to continue to mark all the nodes, how this material was produced, because this would give a big hint. Even negative results are important to find a better way to produce this material. And by the way, this is the excellent review paper in 2014, and it is already cited more than 1,000 times. As if you want to find details, please look at this paper. And then we have the quantum dots. This can be any composite material of in nanosize. So nanosize means less than 10 nanometers. So this shows then the interesting feature. And so I show here in another overview paper the main difference between carbon quantum dot and graphite quantum dots. Also here the broadening of the peak and also the peak position is important. Also the red carbon quantum dot, this is also shown in the high resolution TM picture, is usually considered as best for the photocatalytic properties. Also it is important to collect experimental results from different methods. This is the Raman method, XPS method, photoluminescence, and also XRD and high resolution TEM. Also this is a very systematic study. It is an interesting title, also laser engineered heavy hydrogen carbon. Old materials, coal is an old material and has new opportunities due to the new processing methods. By laser ablation, this material can be splitted into this quantum dots, and the carbon quantum dots consists of graphite, here the nanocrystalline graphite, and here the amorphous carbon. And so this is a systematic change in the bonding structure, and they found a linear combination between the position of the G bands and the D bands. And so also for me, this paper makes it possible to characterize the type of nanomaterial which you have just from the position on the width of the G band. And also this shows now the overview over the different synthesis methods. So we can have a top-down approach from by splitting larger materials into smaller nanomaterials by chemical ablation. This is a very rough method and also usually considered as harsh conditions with poor controllability. But also this parameter is the most important, the quantum yield. Also it means one photon which introduces the comes into the photon process, how much electrons are excited, and also these more sophisticated methods, laser ablation or microwave irradiation, they get a much higher quantum yield, and so also this is important if you want to have a good material processing. Also this is the bottom-up processes. They start from small precursor molecules like this diethylene glycol and combine them under microwave radiation. And this is a very simple and cheap method to cost-effective and eco-friendly to produce good carbon quantum materials. Also, and now in the following, I show some old results which we got. This was actually also a collaboration with India. We processed ceramic materials by Sol-Gel processing, and the peptization process is important. Where you start from a precursor material and then put some acid in, and this means we control the pH value, the acidity of the solution, and either way is good. In the acid condition, we have a lot of ions, metal ions here, and in the hydroxyl pH of a large value between 7 and 14, you have the minus ions in the solution, and both are good for separating the nanoparticles. Also, this is called the stabilization of nanocolloids. If you use ketchup or mayonnaise, you know that the materials should not stick together, but all the nanoparticles should be separated, and this can be done by these ions, pH control, or the second method is by steric stabilization, attach some polymers onto the surface, so this keeps the particle in a distance, and then the depletion stabilization by just adding some other polymers to this solution which don't stick to each other. So all three effects can be combined, and this is how the carbon quantum dots are also produced. And then there are also other interaction effects in the solution. The surface relaxation of nanoparticles. The nanoparticles usually have a larger surface energy, more reactive. Then if you dry your solution, you get the capillarity forces due to the retraction of the liquid, and also due to the bonding angle at the surface. And then the van der Waals forces polarization. And actually, as a function of the distance from the surface layer, we get this complicated potential function. This is DLVO theory shows first a decrease and then a slight increase due to the size of the water molecules. So, and all this is now done also on the carbon quantum dots. This is a book chapter, and of course we usually want to have this situation, random distribution of very small nanoparticles, and while in ceramics we had the closed packed situation. And also this is my senior high school in Germany, where I graduated in a small town in Braunschweig in Germany. And this was named after a famous mathematician, Carl Friedrich Gauss. It was on the German money from 1992 to 2002, before the euro came. And Gauss is very famous for his distribution. The American call it the bell shape distribution, but Gauss distribution. So I always show the students what situation is better, right or left. So the right one is not good, because here you have a broad distribution, large particles as very small particles, and this is bad for the properties. And what you want is a very narrow full width half maximum, and to get this you need to control the growth of your nanoparticles. So it means all particles should have the same time for growth, and so this is usually you have a supercritical solution, and then with one laser beam or one electric impulse, all particles start to grow. And this is the advice for any researcher in this field to use this. And then another thing which is not yet discussed in the literature is the phonons, the thermal vibrations of the molecules also strongly affects also the coupling of the electrons and the phonons is a very important issue, and not yet discussed in the nano materials. And this is the base of the thermoelectric materials and also the microwave resonators. Everybody has now a smartphone. Everybody carries these electron phonon devices with you. And so this is probably the most sophisticated paper on the band structure of the carbon nanomaterials. So we have different issues which we need to consider. The surfactants, it means what kind of polymers are bound to the carbon quantum dots. Also this is there are so many papers which report this already. This is, I think, quite well understood. Then the doping, also by nitrogen, usually is beneficial for the carbon quantum dots. And the defects is not really good understood. This is shown here. As I said, the crystal structure can have many defects, vacancies, or dangling bonds at the surface. And then the interface itself, there are three different types of interfaces where the orbitals just meet each other, where they bend it upwards or bend it downwards. And the design of the interface is still an issue which need to be researched. And then, as I said, the phonons. So I think this is almost the end of my talk. Yes, also this is the outlook carbon quantum dots in future. I said the green synthesis is the big issue of these materials, and if you use natural materials, it is quite likely that you can use it as medicine for your body. Defect control, then characterization by any of these experimental methods. And the high quantum yield is one issue, and the high degeneration rate. But as I said, any basic paper is important. And in our days, if you collect many data and find the entities and relationships. Artificial intelligence is entering material science, but it has not yet entered carbon quantum dots, and so and also the reverse engineering. If you know what you want on properties, then you can easily try to design your material what you need to design these properties. So, and one last OHP for making advertisement for this special issue. This is MDPI, one of the sponsors of this conference, and I am a special editor of photocatalytic technology. The deadline is 31st of May, and any original contribution to the issue of photocatalyst, it can be also the traditional semiconductor ones or metal ones. Any paper is welcome. We have already 3 papers, and I'm looking forward to your contribution. Thank you so much for your attention.